Quick, the two sample difference of means with the t-distribution. So we've talked about constructing a confidence interval for a single mean. Here's how we do a difference of means. It works pretty much the same way as the confidence interval for a single mean. Conditions you have to check for both populations. Needs to be both samples need to be random. You need to check normality for both populations. Each population needs to meet one of these three conditions. Either the population distribution is normal, n is at least 30, or you need to actually check your data for skew and outliers in your sample. Independence, the sample is less than 10% of the population for both populations if we're sampling without replacement, and that the samples are independent of each other, or it's reasonable to assume that they're independent of each other. If they're not independent of each other, then we probably need to do paired data instead, but that's a different video. The standard error for the difference of means is the square root of the sum of the variances of the two sampling distributions. So, right, for one mean, it's s over the square root of n. All right, if that's your standard error, right, your variance would be s squared over n. For two means, you get s squared over n, s1 squared over n1, and s2 squared over n2, and you add those together and then you take the square root, and that's going to be your standard error for the difference of means. Regarding critical value, for a one sample t-interval, we used n-1 for our degrees of freedom. For a two sample t-interval, how many degrees of freedom do we use? There's a very complicated formula for it. As far as I can tell, you don't need to know the complicated formula for the AP test. You would, if you were going to do it, you would do it using a calculator anyways. But as far as I can tell, you don't need to know it. So for our purposes, we're going to use the smaller of the n's minus 1. So, example, researchers at Yale carried out an experiment where they sent out resumes to faculty at academic institutions for a lab manager position. The resumes were identical, except that on half of them the applicant's name was John, and on the other half the applicant's name was Jennifer. Unlike in the match pair scenario, each faculty member received only one resume. So there's no paired data, right? These two samples are independent because they went out to different universities. So we're comparing the mean salary offered to John relative to the mean salary offered to Jennifer. So we're going to find the average of each group separately and take their difference. And then we're going to construct a confidence interval on it. All right. So our 4-step procedure, we state the parameter, which is the average, which is the difference between the average salary offered to John and the average salary offered to Jennifer. Between the average salary offered to John and the average salary offered to Jennifer. And our confidence level is 95%. This is a two-sample t-interval. T-interval for, we'll say, mu1 minus mu2. or mu John minus mu Jennifer. So 2-sample t-interval for a difference of means. And we check our conditions. Is it random? Yes. Right, the resume, they said not resumes, it doesn't say how in the specific part, but it was random. In the full write-up of the experiment, it was random. Independent. Dependent. It was independent. And we have N1 is greater than 30 and N2 is greater than 30. So that's our conditions. We are going to state our general formula, right, which is for a confidence interval is always the point estimate plus or minus the margin of error. And then the specific formula is going to be x bar 1 minus x bar 2 plus or minus t times the standard error, which is s1 squared over n1 plus s2 squared over n2. So we'll make John B1 and Jennifer B2. So 30,238 minus 26,508. What is our t value going to be? We can do that on the calculator. Do the inverse t with 62 degrees of freedom, because our n is 63 here. And 95% confidence means 0.025. So that gives us a t of 1.999, or basically 2. And then the square root of 5567 squared over 63 plus 7247 squared over 64. And so the difference in the means, in the sample means, 30,238 minus 26,508 is a difference of $3,730. And when we plug this whole horrible looking thing into our calculator, we're going to get that the margin of error is, please hold, 3 plus 7247 squared over 64. I get a margin of error of $2,290 and 18 cents, but I'm going to round to the nearest dollar here. So that means that my confidence interval is going to be from $1,440 to $6,020. And I don't really have room on this slide to write the conclusion, but the conclusion, we are 95% confident that the difference between, or that the interval from $1,440 to $6,020 captures the true difference between the average salary offered to John and the average salary offered to Jennifer. Another example, an instructor decided to run 2 slight variations of the same exam. Prior to passing out the exams, she shuffled the exams together to ensure each student received a random version. So there's the random condition. Anticipating complaints from students who took version B, she would like to evaluate whether the difference observed in the groups is so large that it provides convincing evidence that version B was more difficult on average than version A. So we're going to make a 95% confidence interval. So state the parameter is going to be the difference in average score on exam A and exam B. Our confidence level is going to be 95%. Our test is a 2-sample t-interval for mu A minus mu B. And then our conditions. It's random because it said that it's random. The 2 samples are independent. This is an experiment, so if there was randomized assortment of groups, the should also be independent, and our n is at least 30, n1 is 30, and n2 is 30. So that checks our normality condition. Our general formula is, as always, the point estimate plus or minus the margin of error. Our specific formula is going to be x bar A minus x bar B plus or minus the t times the square root of SA squared over NA plus SB squared over NB. So that's going to be 79.4 minus 74.1 plus or minus our t. We're going to do the inverse t with 29 degrees of freedom. And so that's 2.045 square root of 14 squared over 30 plus 20 squared over 30. And so our difference in the x bars is going to be 5.3. And we plug our whole horrible margin of error calculation into the calculator. 14 squared over 30 plus 20 squared over 30, and get a margin of error of 9.11. So our confidence interval is going to be from negative 3.81 to a positive 14.41. So our conclusion, we are 95% confident that the interval from negative 3.81 to positive 14.41 points captures the true difference in the average scores on exam A and exam B. Does this provide evidence that exam A was harder than exam B, or exam B was harder than exam A? No, because 0 is in the confidence interval, so it is plausible that there is no difference in the average scores. And that's it for the difference of means.